This is the fourth inclined plane without friction video. The aim of this video is to solve a problem in which a horizontal external force is applied to a block on a smooth incline. The end of the video provides a second question for practice. Get straight to the example. Example 1. A 28 kilogram block sits on a smooth surface that is inclined to an angle of 15 degrees. The block is subjected to a horizontal force P. So we can put this together before looking at the question. So we've got our block. It's on an incline of 15 degrees, definitely not drawn to scale. And the weight of the block is 28G. There's a reaction force. And then there's a horizontal force applied to this. To tell whether it's acting to the right or the left, we need to see part A. Calculate the size of P if it holds the block stationary. So if it's holding the block stationary and it's horizontal, it's got to be pushing to the right. That's P. We've got that. As it's holding it stationary, we don't need to put the acceleration arrow onto the picture, and we can go straight into resolving forces. So we resolve forces up the slope. I'll apply Newton's second law in that direction. We need one other angle, that's 15 degrees. We can tell that because we've got a Z angle case here. So these two angles have got to be equal to each other. We need the component of P that acts up the slope and parallel to it. So if we take P, it acts like that. Here is the parallel component of P that acts up the slope. There's the 15 degree angle. Here in yellow is the component of P that acts into the slope. So the green component here, the component that acts along the slope, is the adjacent. So we would deal with P cos 15 degrees there. As that, the full force there is P. The other component, the one into the slope, the yellow one, this would be P sine 15 degrees. Sine because it's the opposite in that triangle of forces. Okay. So acting up the slope, we've got P cos 15 degrees, and acting down the slope, so negative, we've got 28G sine 15 degrees. That component is this one here. That's the 28G sine 15 degrees. Together, they are the only forces that act parallel to the slope, so they make the resultant MA. The only thing that's unknown here is P, as A is known to be 0. It's at rest, it's stationary. So P cos 15 degrees minus 28G sine 15 degrees is 0. Rearranging this by putting 28G sine 15 degrees on the right and then dividing by cos 15 degrees will leave us with 28G tan 15 degrees. That's the P, the value of P that's required to keep the block stationary. This is 73.53 newtons. That's the answer to A. In part B, we've got calculate the size of P if the block, starting from rest, travels 4.7 meters down the slope in 8.3 seconds. We should just draw another picture here. So in part B, this does slide down the slope. So it's got to be accelerating down the slope. Still got a reaction force acting on it. P still acts on it, but we don't know how large it is. It's got to be smaller than the last case because it's allowing this to slide down the slope. We've still got weight. The block's mass hasn't suddenly disappeared. That's 28g. Okay, we'll be resolving down the slope parallel to it because the acceleration is directed that way. P cos 15 degrees, just like before here, it still acts up the slope, it just isn't going to be as large, and so that's negative now because we've decided down the slope's positive, and then plus the component of weight, which still acts down the slope, plus because down the slope is negative here, so that's 28g sine 15 degrees, and that's equal to MA 28A, it's a 28 kilogram block. Okay. The only unknown here is P. The unknowns here are P and A. So with one equation we can't find either of those, so we need something else. Going back to the question, a distance covered, a displacement along the slope, and the time it takes are mentioned, so we can use SUVAT. So again, down the slope is positive, SUVAT, S-U-V-A-T. It's going to travel 4.7 meters down the slope. It's going to take 8.3 seconds to do that. This block starts from rest, U is 0. V we don't know and won't try to work out. The acceleration we want to know, because if we can find the acceleration here, we'll know it there, and then this equation will only have one unknown and we'll be able to solve for P. So we'd like the equation that doesn't have V in it. That's S equals ut plus half at squared. U is 0, so S 4.7 is equal to half at squared, half multiplied by A, multiplied by 8.3 squared. Okay, that is equal to 0.136 meters per second squared. Updating where necessary, 0.136. That acceleration is directed down the slope, so it should be positive following that direction. We can then work on this equation here. So minus P cos 15 degrees plus 28g sine 15 degrees is equal to 28 multiplied by 0.136. We need to make P the subject of the equation. The 28g sine 15 degrees minus 28 times 0.136 is equal to P cos 15 degrees. And then we can divide both sides by cos 15 degrees to isolate P. P is equal to 69.6 newtons. We can check this is reasonable by looking back at the last part. 73.53 was needed to hold it still, and a slightly smaller force of 69.6 allows it to accelerate down the slope at a slow rate. Okay, that's the end of example 1. So we'll go over and look at another example. Example 2. In example 2 we have a 330 kilogram block and it sits on a smooth slope that is inclined to an angle of 42 degrees. The block is subjected to a downward vertical force of Q newtons. This is a good opportunity to pause the video and have a go at setting this question up and then trying to answer parts A, B and C. I will now go through and deal with the question. So before looking at A, B and C, we can just draw the relevant picture. So we've got a 330 kilogram block. So it's got a 330 G weight acting straight down, a reaction force R acting perpendicular, and then there's this force of Q newtons that acts straight down on the block, like that. So not horizontal like the last one, but vertical. This slope is inclined to 42 degrees. Therefore, the angle in there is 42 degrees. If we look at these straight lines here, the angles between them are the same either side. So that is also 42 degrees. That will turn out to be very useful. And this block accelerates. In part A it says calculate the acceleration. We'll assume acceleration is down the slope. If we're wrong, it won't be a problem. We'll just get a negative value. So we can resolve forces along the slope, so parallel to it and acting down to follow acceleration, and apply Newton's second law. So we know that this component of weight acts parallel to the slope and down, so that's 330 G sine 42 degrees. So 330 G sine 42 degrees, and then we should break Q down. So Q is like that, and then there's the surface. So that's Q. If we look at the parts of Q, so there's a component of it that acts straight into the slope, and then there's a component that acts parallel to the slope and down. As it's parallel and down the slope, it's also positive in the equation. And we've got the angle of 42 degrees here. So this component, the blue one, one that's opposite, would be Q sine 42 degrees. When we use opposite in these triangles, we'll always be using sine. So we add Q sine 42 degrees. Both of those, both Q and the weight, are working to drag this down the slope. They're the only forces that act along the slope, or the only components that do. So together they make MA. We know that M is 330, so 330 A. Q is 2,200 in this situation, so we can put that in. 330 times 9.8 times sine 42 plus 2,200 times sine 42 equals 330 A. A is now the only unknown, and it is the aim of the question. A equals 330 times 9.8 times sine 42 plus 2,200 sine 42 all over 330 is equal to 11.0 meters per second squared. That's the answer to part A. Part B doesn't change the situation at all. So Q is still 2,200, but we would now like to know the reaction force when Q is 2,200. So carrying on down, R lies in the perpendicular to the plane direction, so we'll resolve forces and apply Newton's second law perpendicular to the plane. So we can see R acts straight out of the plane. It follows this direction. So we write R. Then Q, if we look at its components, this green one here, that's just been highlighted, that is acting straight down into the slope. So that's negative. If we steal that component and place that against the arrow here, you can see it points down and into the surface, whereas the direction we're resolving in is up and out of the surface, so it will be negative. So we've got minus, and then we need to work out what that component is. It's the adjacent in the triangle there, so it's q cos 42 degrees. So minus q cos 42 degrees. In addition to these components, there is a component of weight that acts into the slope. So that's this purple component here. That's 330 g cos 42. That's acting into the slope, so it's negative as well. 330 g cos 42 degrees. And together they're all equal to 0. This doesn't accelerate into the slope or out of it. So you can rearrange 2200 cos 42 plus 330 times 9.8 cos 42 is equal to R. Therefore R is equal to 4040 newtons. So we've got part B. Okay. Then the question changes. The magnitude of Q is changed. It could be larger, it could be smaller, but it still acts in the same direction. So part C, the reaction force is 2,800 newtons. Calculate the time it takes the block to reach a speed of 13.7 meters per second. Okay. So part C, calculate the time it takes. So we're looking at SUVAT, S-U-V-A-T. We know that this accelerates down the slope from previous parts. There's no Q applied in this direction. There's no way it could ever cause acceleration up the slope. The distance we don't know and probably won't work out. The initial speed is 0. This starts from rest. It gets up to a speed of 13.7 meters per second down the slope. The acceleration we don't know, because it's not this value here, because that was the value when Q was 2,200, but now Q has changed. So we don't know that. And the time is what we are after. Calculate the time it takes. So we'll put a question mark there. So we need to know acceleration. We need to know three things to make use of a SUVAT. So if we want to get the acceleration, we need to go back to the forces. So we apply Newton's second law parallel to the slope. So we have got, it's the same setup as before, so we can pull this line straight down. We've got R minus Q cos 42 minus 330 G cos 42. It is still equal to 0 because no matter whether it slides along the slope, it doesn't accelerate into or out of the slope. That equation has two unknowns, both R and Q, but the reaction force we're told is 2,800. So 2,800 minus Q cos 42 minus 330 G cos 42 is equal to 0. So Q is the only unknown. We can solve for Q. So I'd have 330 G cos 42 minus 2,800 is equal to minus Q cos 42, or more usefully, Q is 2,800 minus 330 G cos 42 all over cos 42. So we'll know Q in this case. Q must be 533.77 newtons. Okay. Then we can resolve, the wrong sign has been used up here, we're resolving into, so out of the slope, like that. Then if we want to get the acceleration, we need to consider the applying Newton's second law parallel to the slope, and we'll work to the left. So here we will have, if we look back at the original equation, 330g sine 42 plus q sine 42 equals 330a. Because it's still the same setup, we haven't removed any of those forces and we're still resolving down the slope. So 330g sine 42 plus q sine 42, and that's equal to ma 330a. We know q is 533.77, so 330g sine 42 plus 533.77 sine 42 all over 330 is equal to a. So the value of acceleration is 7.64 meters per second squared. So that's now the information we needed. It took a while, but it's the information that we needed to fill in here. Again, it's always easier to deal with it if we write it in where it belongs. So then we can just use a Suvat equation that doesn't have s in it, so we use v equals u plus at. V equals u plus at. Oh. V equals at, so that's 7.64. T is equal to 13.7. So the time that this takes is 1.7 seconds, and that's the end of example 2.